Okay, so you've watched the videos and you've done, you looked at the sheets, you did your own GeoGebra, you watched the video I posted of, rotating like a line or a parabola or a function about the x-axis and around the y-axis. So you know what we're doing. Once again, the idea is we're rotating like a line or something around the x-axis. We're creating a solid, and the first thing is we want to know what is the volume of that solid. Like how much water could we pour in the bowl? The other thing we're kind of doing is we're taking like two functions and like rotating it around. And the idea is like, it's like we need like how much clay do we need to build like a vase? We're not concerned about what goes inside, but it's almost like the volume between like the two curves. So that's what we're looking at. So let's just jump into let's talk about the math behind it. We know visually what we're going to do. So we call it volume of rotation. And so the first question we're going to do is we're going to take f of x equals x from 0 to 3, and we're going to rotate it about the x-axis 360 degrees, 2 pi. I'm really bad at like going back and forth. 360 degrees, and we want to find the volume. And so the idea here is, once again, we saw it from Desmos. Here's the line, y equals x from 0 to 3. And the idea we saw is that we're going to rotate it around. So we actually have a cone. And the question is, how do we find the volume of this cone? Well, first of all, you should know, So let's think about this. When I asked you to find the area under the curve, I said we were adding up the rectangles. So in this case, it's still that idea, but if you notice, I created like these discs or circles. And so the idea is that there's these discs with like infinitesimally small thickness, but they're circles. And so what I'm doing is I'm adding up all the circles from 0 to 3. So usually I said it's all about the rectangles. In this case, it's all about the radii, the radius, right? So the question is, what is the area of all these circles? Well, the area of a circle is pi r squared. In this case, the radius is the function. The radius is the function at the specific location. So this first circle here might be a radius of 0.5. Right here, the radius may be 0.1, 2, and then 3. So to find the volume, therefore, it's the sum from 0 to 3 of pi r squared. And that's how we find the volume of this rotation, or the volume of the cone. Obviously, if I was here, I'd make you actually come up with a formula for the volume of a cone, where this is h, and the r is like the radius. But we're not doing that right now. So let's figure out this problem. So we have generally what they do is they pull out the pi, leave the integral from 0 to 3. F of x, each of the radii is x squared dx. So we have pi x cubed over 3 from 3 to 0. We're lucky because we have that 0, so it's pi 3 cubed is 27 divided by 3, it's 9, minus 0. Final answer, 9 pi. Let's try another example. Let me move the computer over. Let's try another example. This time, let's take the y's radical x from 0 to 4. Let's make it from 1 to 4. And let's rotate that also around the x-axis. So let's see, let's rotate 360 degrees around the x-axis, and then find the volume. Find the volume. Well, we can make a quick sketch. We kind of know the radical goes like this, but we're not interested in starting from 0. We're kind of like starting from here. So we're going to rotate it this around. We have this interesting shape. And now we can find the volume. It's like a big bowl, a big bowl or something with its really thin sides. And that's what we're interested in. How much water can I pour in this bowl? Well, let's see. We have the circles. We know that it's like the way I described in geometry, to find the volume of a cylinder, it's like stacking up pancakes. In this case, the pancakes are getting larger and larger. So we have a bunch of circles, discs, right? And once again, it's all about, well, this is not the pen I like. So it's all about the radius. It's all about the circles. It's all about the rectangles. Always comes back to rectangles. In this case, the rectangles are just the radius. So let's see. So the radius. So radius is radical x. So let's put it together in the formula. The sum of all the circles. So the integral from 1 to 4 of pi r squared dx. Can you see that? There we go. Nice. Once again, I recommend that you go to Desmos and you literally make this so you can see about it. Let's figure this out. Well, this is nice. It's x. So it's the integral of x from 1 to 4 dx. Nope. So we have x squared over 2. I'm sorry, I forgot the pi. Don't forget the pi. From 1 to 4. So we have pi times, let's see, 16 divided by 2 is 8, and minus a half. So it's 15 pi over 2. So we can rotate it around. Let's try another one. Let's try one with trigonometry. Sorry, guys. I want you to rotate y equals sine of x 360 degrees around the x-axis. So let's take y equals sine of x and from 0 to pi and rotate 2 pi around the x-axis. Find the volume. Well, first let's make a picture. That's the full sine wave. I don't want the full sine wave. I only want pi. Right? So this is pi. And I'm just going to rotate this thing around. You can do it in Desmos. You can do part of the curve, the whole curve. The idea is you're creating this solid, and we want to know what the volume is. So let's, looks like that. So it's once again, it's another interesting shape, but now it's not exactly like a sphere. It's a weird shape, but now mathematically we can figure out the volume of this. So we know that it's pi. Once again, it's all about the rectangles. So we have these discs, and we want to know what the area of these circles are. It's changing. It got bigger, and then the new discs got smaller. That's fine. So it's pi, integral from 0 to pi of pi r squared dx. So it's pi 0 to pi of sine squared x dx. We know from the last unit how to find sine squared. it might be in the book, but you can do this on your own. We recall that the cosine of 2x is equal to 1 minus 2 sine squared x. So let's see. So 2 sine squared x is equal to 1 minus cosine 2x, and that means sine squared x is equal to 1/2 minus cosine 2x over 2, and we can do the math. You can do this by hand. Expect something like this to be on a part 1 question. So we have pi from 0 to pi of 1/2 minus cosine of 2x over 2 dx. And we're ready to integrate pi, x over 2 minus, we know that we're going to be substituting the 2x, and that 2 is going to end up in the denominator, and the integral of cosine is sine. So it's sine 2x over 4. Try it on your, once again, remember, make a u substitution. Du over 2 equals dx, so that 2 ends up down there, and then we know the integral of cosine is sine. From 0 to pi, we're lucky here. We're lucky. I can see already that the 0 is going in here, and sine of 0 is 0, so I'm lucky. So it's pi over 2 minus sine of 2 pi over 4 minus 0. Well, we're even more lucky because sine of 2 pi is sine of 0. 2 pi is like 0. Sine of 0 is 0. Final answer, pi squared over 2. Yeah, nice. Okay, so you're saying, hey, Mr. Adler, if we can rotate around the x-axis, can we rotate around the y-axis? And the answer is, yeah, you can. So I want you to take y equals ln of x from, 2 to 5, and I want you to rotate about the y-axis through 2 pi, 360 degrees 2 pi. So let's think about this. Let's think about this visual. So we know what this looks like. We know that this is ln of x. This is y equals ln of x. We know that this is 1. Therefore, 2 is somewhere in here, right? And 5 is somewhere over here. So the idea is we want to take this part of it and rotate it about the y-axis. Once again, if you need a visual, go to GeoGebra, put the function in, 2 to 5, but then rotate to the surface, the rotation for y-axis, and you'll see it looks something like this. It's over here, something like this. Okay, that's fine. So I still have my volume, and I still have, like, my pancakes or my discs getting larger. My pancakes or my discs still have a radius. The question, though, is, I'm not in the world, because I'm rotating around the y-axis, I need to convert my function into terms of y. So first of all, I need to know where my pancakes start, and I need to know where my pancakes end. Well, my pancakes start at ln of 2, and they end at ln of 5. Okay. Next, I need to know what my radius is. Well, I need to know what my radius is, right? This is easy. Just rewrite this in terms of x. So if x takes me to y, then simply e to the y equals x. So this radii is e to the y. Right? So this is what I'm interested in. So my radius is e to the y, right? So It's pi r squared dy, and that's fine. And now they're purposely going to give you something like this, so it works out nicely. They might give you like a sine and ask you to rotate on the y, and you go, I can find the integral of arc sine or cosine, or you can find the integral of arc tan. Just pay attention. Well, this is very straightforward. We have, this is pi e to the 2y over 2 from ln of 2 to ln of 5. Once again, you're just integrating e to the 2y. That's a basic integration. And then we have, let's see, this is equal to pi. I'm going to pull out the 2. We have e to the 2 ln of 5 minus e to the 2 ln of 2. Final answer. Can you see that down there? Can you see that down there? Yeah, that is, let's see, that's 25 minus 4, 21 pi over 2. So once again, if you're in the world of x, your function is f of x. And the pancakes, they just start at the x and end at the x value. Sorry. If you're over, I apologize. Once again, if you're rotating around the x-axis, your radii have to be a function of x. If you're rotating around the y-axis, your radii should be a function of y. It just makes your life easier, and the problems work out nicely like this. You're not going to be asked something that's really confusing. Also, please remember that if any of these are asked on a part 2 question, all you have to do is write the formula down. All you have to do is write the formula down and then hit GDC. Okay, let's do another problem. Now, the last thing, nice. The last part of this is, maybe you've seen in other textbooks, is the last part is they're going to give you 2 curves. So you're going to find the region between 2 curves, right? And then second, rotate this region about the axis, 360 degrees, and I say find the volume. This is weird. So in this case, for example, they're going to say f of x equals radical x, and g of x equals x squared. They're first going to say find the point, find the intersection, and then they're going to say rotate about the x-axis, 302 pi, and find the volume. So what does this look like? So you say, okay, Mr. Other, I can quickly sketch this. You know that this is a radical x. Here's the parabola. You know either by inspection, just by looking at it, you know it's 0, 0, and this is 1, 1. And so the idea is, it's kind of weird the more I think about it. The idea is you're taking this region and you're rotating it around the x-axis. I'm not even, you know what? Yeah. What you can do is you can put f of x in the first, g of x in the second, and then rotate both, do the same thing where you get an n for both of them, and then you create 2 surfaces. The first one for f of x, the second one for G of S, and you can literally see like this like flower petal. Sorry, you can literally see this like flower petal like moving around. I can't even draw it. It's ridiculous. Well, I guess I can draw it. It's like you imagine this like flower petal like moving around the x-axis. The question in this case is like how much like clay would we need to make that thing? And so the logic behind it is you would say, okay, the upper function would be the first. The upper function would be the first volume I would find, and then I would take away, I would subtract all of this. So the idea is if you're given two functions, in this case, you're given, so let me ready for the generalization? Either you're going to have, like finding the area between two curves, you're finding the volume between two curves. It's the same idea. Oh, same idea, exactly, I'm sorry. So the volume is equal to pi integral, it's either up squared minus upper squared minus lower squared dx, or right squared minus left squared dy. And in the same way, either this is the x or x2, y2. It's the same idea. It's the same idea like volume. The only difference is you're not squaring the difference. You're taking the upper curve squared minus the lower curve squared. Or, if you're in the world of y, you're taking the right squared minus the left squared. They're probably not going to ask something like this. And so we can see an example like this on page 671. Let's move the camera over. In the book, you'll see a question like this. They'll say, this is 20 example in chapter 27. They'll say y equals x squared plus 6, right? And they will say the other curve is y equals 8x minus 8 squared. And they will say, find the intersection and then rotate this region about the x-axis. So you kind of know what the sketch looked like. You say, okay, I know this is a regular parabola, but shifted up 6. So I know it kind of looks like this. And this is the parabola. I can factor this. You know, it's x minus 8. I kind of know that you're an 8, and therefore I know it goes up and then it comes down. Right? So this is y1, y2. Sorry. And so the idea is, first of all, we're going to find this region, and we're going to rotate it. First thing we have to do is we have to know the limits of the pancakes, or the limits of the circle. So first thing we have to do is find the intersection. So x squared plus 6 equals 8x minus x squared. 2x squared minus 8x plus 6 equals 0. X squared minus 4x plus 3 equals 0. You know where this is going. X minus 1, x minus 3 equals 0. X equals 1 to 3. You start to write it out. You go, okay, Mr. Adler, the frown is on the top. You're like, this is the up. Just like finding the area between two curves, this is the upper, this is the lower, and so you're like, okay, if I take this thing, whatever this thing is, and rotate it around the x-axis, I know it's pi the integral from 1 to 3, because remember, don't forget, it's always about the rectangles, and these rectangles are going to be the radii. So it's the lower, the upper, squared minus the lower, which is the smile, dx. Now the book says, show that it's this whole, the first thing they say is prove, and you can read it, they say prove it's, the integral is supposed to be pi from 1 to 3 of 13x squared minus 4x cubed minus 9 dx. And then you notice, and then they say, find the volume. But you notice something. You say, hey, wait a minute, Mr. Adler, this is a part 2 question. So you know what? The only thing you have to do? Stick that in the calculator. Please make sure that everything's in parentheses. Stick it in the calculator, and the answer is 184 units cubic units. Now, how are we doing for time? Perfect. Let's finish up. Let's finish up with the original problem. And the original problem is a part 2 question, so I'm just going to create the integral, and then we're just going to put it in the calculator. It goes something like this. We were told that we were told this first function, it kind of was like this, and then went up like that, and then this function kind of like went here and up like that. And the idea was, let's see. So what did we have here? We had y. This was y equals x squared plus 1. Yes. And this is y equals x minus 1 squared, right? And we were told to rotate this around the y-axis. So we know what this looks like. You can take both of these and rotate it, and you kind of look something like this. Right? And so the idea is, what is the volume? How are we going to figure out the volume of this? And once again, we knew this was 9, right? Yes. The question is, how do we know what the volume is? So the idea is, I want you to think about it for a second. So the idea is, we're going to rotate it around the y. So it's rotate around the y-axis. So what we have to do, now this is a little different. So it's not exactly like the problem where we found the intersection and we rotate it. What we're going to do here is we're going to take the outside and rotate this around, and then we're going to subtract off the inside. Now, the reason we can't do it together is because the limits are a little different. The outer one, this one, the y equals x minus 1 squared, this starts at 0 and goes up to 9. But the inside, this little parabola here that we're going to like carve out, that one starts at 1 and goes up to 9. So, it's easy. Next, we're in the world of y, so we have to turn it. So, the first thing we have to do is convert this. So I'm going to start with my y equals x minus 1 squared. This is y squared plus 1 equals x. This is the f. Let's take a look at g. G is y equals x squared plus 1. So x is equal to the square root of y minus 1. Now we're ready to go. So what is the volume of my big What is the volume of my big, like, the outside of the vase? So that's the integral from 0 to 9 pi r squared dy, and so that's the outside. That's the big volume here. But the idea is I want to scoop out the middle, or that inside. I just need to know how much clay to make. So I need to take away that inside part. So that's from 1 to 9 of the square root of y minus 1 squared dy. Sorry, I made a mistake. No, I apologize. This is the square root. Sorry. This is the square root plus 1. So it's the square root of y plus 1. And so you're looking at this whole thing. You're looking at this one thing and you think, this is going to be really tedious. Well, you know what? It's not, because it's a part 2 question. Stick it in your calculator. The answer is 168. Is that right? That is it. You can do the problems in the book, and that's the end of the unit.